This is the first in a series of tutorials that introduce submodels, which are the building blocks for creating models of greater complexity and for creating more sophisticated types of models, such as spatial and agent-based models. In this tutorial, I will show how we can create one or more submodels, why you might want to do that, and the mechanics of embedding a submodel into a parent model. Submodels are the answer to managing complexity when we can factor a complex model into manageable submodels with well-defined interfaces. In subsequent tutorials, we will learn how the submodel structure is used to create interesting spatial topologies for Numerus simulations. For example, Numerus provides 2- and 3-dimensional lattice grids in which each cell is an instance of some submodel. Submodels are also used in Numerus's individual-based modeling architectures by having each agent be an instance of some submodel. I will now ask my friend Andy to discuss submodels and show you why they are so useful. I will then return to take our logistic model from an earlier tutorial to illustrate how a submodel can be created and used in Numerus.
Conceptually, you can think of a submodel as a discrete piece of a larger process. Submodels function a little bit like black boxes that basically operate on their own, taking inputs, doing something or other with those inputs, and then spitting out some outputs. So here we see a fancy piece of equipment that is doing some kind of complicated process with water. But we can clearly see that this complicated process really consists of many subcomponents where different things happen. And we can think of the individual components as submodels, in which processes take place internally, governed by their own parameters and with their own dynamics and so forth. And what happens in one component is essentially independent from what happens in other components.
Numerus
Allows us to design models with this metaphor in mind, which is a really useful thing to do because it helps us to understand and visualize how a big complicated system operates as a whole, but we can still open up these submodels if we want to, examine their details, take one out and swap in a different submodel, save a submodel to use in a different model, and so forth. And as we'll see in a future tutorial, the same functionality is also what allows
Numerus
to create more sophisticated spatial models and agent-based models in which each agent or each grid cell is essentially a submodel. Let's look at an example where using submodels might be useful for improving visual clarity and understanding how a modeled system operates. In the past, we've been working with relatively simple models like this Beverton-Holt population model. In this model, there are only a half dozen or so components. It's really easy to see what is connected to what, and there's plenty of room on the model canvas to add a display component such as this graph. We could even add sliders up here if we wanted to, and the model would still be very easy to operate and understand. But as the system gets more and more complicated, or a modeling objective drives us to represent the system in more and more detail, our model can quickly get very unwieldy. What we're seeing here is an age-based model for a fishery, where the fish population has been divided up into separate age classes and has various parameters for things like survivorship and reproduction, net size and catch rate, and so on. Now this schematic is from a program called Berkeley Madonna, but if we were to build it, it would look pretty similar. And it's actually not that different than the simple population model we were just looking at. This is not a fancy agent-based model. We're still keeping track of the total population, only now that we have divided it into separate age classes, represented by these different stocks. We could move these components and connectors around to make this look a little bit less like spaghetti, but we can't get it a whole lot cleaner because there's simply a lot of parameters. And many of the parameters we need to have a value for each age class. This is a perfectly good model. It runs great and answers the question, but you can imagine if you were getting an error and had to debug something like this, or maybe you wanted to change part of it, you're really going to need a lot of time, patience, and concentration. If we were to make this model, it might look something like this. Here, we've taken each of the population models for each of the age classes and created them as submodels that we see listed down here that are embedded here in the parent model. In the parent model, the submodels appear in functions as black boxes. They have inputs and they spit out outputs. And they're all connected together and feed into the stock component down here that keeps track of the total harvest. There are still a lot of connections here, but this is a whole lot easier to follow than before, because not only are the innards of each of the submodels hidden away, we've also buried most of the parameters in the submodels, leaving only the parameter that we want to play around with, which is net size. And if we want to look at the details of one of the submodels, all we have to do is to select it down here in the capsule set, and it appears in the model canvas. We can also run each of the submodels independently, which is a great way to develop and troubleshoot your model. For example, I could add a graph component to this model, double check the initial values, and run the submodel. And this is a great way to see if the model is working properly. This makes it a lot easier to isolate problems so you can fix them than when you have one gigantic piece of spaghetti. For even more complex systems, you can even have submodels that themselves have submodels. That's a little more complicated to analyze, but if you were studying a system that has nested processes that operate at different scales, this could be very useful. The other advantage of breaking a model into submodels is that it makes it a whole lot easier to sort of modularize your modeling projects. Let's say, for example, I really like this part of my model, and I want to use it in a different model. Go to the File menu, click Export, and save it to disk. Then when I'm ready to import that capsule into a different model, I simply go to the File menu and click Import, and it will appear here in the capsule set.
Thank you, Andy. Let's now return to the logistic model we built in the previous tutorial. Recall that the final version had sliders to allow us to change parameters at runtime and a graph to show results. We want to turn this model into a submodel in which the three parameters, R, K, and init, are inputs, and the result, P, is an output. Numerus provides a number of tools to help us with this transformation. The first step is to create a new capsule that will serve as the parent model into which the submodels will be embedded. We do this by clicking this plus button, which creates a new empty capsule under our logistic capsule. Now, since we want this to be the main level of the new model, we simply use the mouse to rearrange the order of the capsules. Actually, this turns out not to be necessary since Numerus could figure out the order once we create the submodels, but it illustrates the fact that you can control the ordering in the list. This 3D animation illustrates the idea that the new capsule, multi-logic, has been created as a layer above the original logistic capsule layer. We've named our new top layer multi-logistic. So let's now save it in a file, which is also called multi-logistic. We are now ready to rebuild the logistic layer as a submodel. The first step is to move the controls and displays to the top level. Let's start with the sliders. Select the sliders and visit the Tools menu and choose Pull Up. They seem to have disappeared, but visiting the multi-logistic level proves that they've only been moved up one level. Actually, this was simply a cut and paste operation. So if we return to the logistic level and click Paste from the Edit menu, they will reappear. We want them back so we can convert them to terms. By selecting In Pins on the Term Property panel, and notice we can do this with one action by selecting all of the terms, we have made these into a special form of term called an input pin. As you might guess, these act as the input interface between a submodel and its parent. Now we continue by using Pull Up to move the population graph to the multi-logistic level, and we see that it has arrived safely. Finally, we need to add a term which we will call Pout, whose value will be P, and we will convert this to an output pin. Output pins serve the function of providing output to the parent level. We can now proceed to create a submodel. Returning to the multi-logistic level, we simply drag the logistic entry in the capsule list to the canvas in the same way we would drag a component or slider or graph. What appears is called a chip, and it can be treated like any other object on the model canvas. Notice that the chip has small lines or pins on its left and right side. These correspond respectively to the input and output pins we created before dragging the chip onto the canvas. Don't worry if you forget to create the pins or want to add more or remove some pins after you've added a chip, because the chip will adjust its pin count as needed. Connecting the sliders to the pins is similar to adding components to a graph. Select the chip, and in its property pane will be a table with a list of input pins. Select a row in this list and then either use the selection menu or right-click on the appropriate input, which in this case is a slider but could be a term, stock, or any other value-producing component. Then we select the population graph as before and either choose from the selection list or right-click the output from the chip. Referring to our earlier 3D schematic, we can visualize the placement of the chip representing an entire submodel on the main capsule level. We should save our work and then fire up the simulation. It should look familiar since it is functionally equivalent to the original logistic model. Suppose now we want a second independent logistic model with different parameters. In other words, a separate set of input sliders. First, to help us distinguish the two sets, we'll rename each of the current sliders so they end with _0. Notice that if we first delete the caption, the new name will migrate and give us a 0 at the end of the caption as well. Now we select the three sliders in the chip, visit the Edit menu, click on Copy, then click on Paste, and we duplicate the chip and the sliders, and all we have to do is add the new chip to the population graph. The schematic now shows how a pair of chips are derived from a single submodel. After saving, we launch the simulation and see two logistic functions with two separate pairs of inputs. Now, Numerus also provides an alternate approach to building submodels the way we just did that is even simpler. Often a submodel candidate like Logistic has been built and tested containing its own set of input sliders and output displays such as graphs or tables. If we wish to create multiple instances of a model with separate inputs and possibly a single display, such as we have just done, there is a shortcut we can use. Start by selecting the sliders, and instead of pulling them up to the upper level, we check the pinned box. Ordinarily, a slider or graph in a submodel is ignored, and in the case of a slider, its initial value is used as if it were a constant. When a slider is pinned, we are telling Numerus we want that slider to appear in the runtime frame. Similarly, we check the pin box for the population graph so that we can get it to appear in the frame as well. Moving to the top level, we pull out one or more chips. Notice that these have no pins, but since we've pinned the sliders and graph, we expect those sliders and graphs to appear at runtime. Now this would seem to present a problem since the number of sliders would be 3 times the number of chips, and so having 3, 4, or 5 chips could significantly clutter the input panel. The problem is solved by using multi-sliders. Each multi-slider handles the same parameter for the entire set of chips. A list of the chips appears below the multi-slider, and so to change a parameter for a particular chip, simply select that chip and make the adjustment. In this case, you'll see that we have separate graphs appropriately labeled. But with many chips, this too can become cumbersome. Returning to the logistic capsule, and again selecting the population graph, we check the multi-display option. Now, when we launch the program, we get a single graph containing all of the output. It is now easy to include as many additional instances of the logistic model we want by dragging chips to the canvas. To summarize, we've learned two approaches to creating submodels from existing capsules. In the first method, we create a new parent level, move existing controls and displays to that level, replace them with input and output pins at the submodel level, drag one or more capsules onto the canvas at the parent level to create chips, and connect the chips to other components. In the second method, which is most useful when a complete set of displays and controls exist in the submodel capsule, we leave those displays and controls at the submodel level, check the pin box on each of these, and possibly the multi-display box, and continue as with the first method at the top level, dragging chips onto the canvas and making necessary connections. This completes our tutorial. See you again soon.